Okay, good morning, everybody. Let's get going. I hope you enjoyed the guest lecture from the other Josh last Thursday. Josh Powers, one of my PhD students. We're going to carry on today by starting in on the second theme of the course, which is the design processes and specifically how they relate to HCI. Before we do, let's talk a little bit about the deliverables. How many people have finished deliverable 1? How many people have finished deliverable 2? Okay, I see almost all the hands up, so we're more or less on track. Again, there are very few of you remaining that are still struggling with installation issues. If you still are and you haven't come to see me, please do let me know where you are. Okay, so hopefully you have deliverable 1 and deliverable 2 under your belt, where, as you figured out by now, those two deliverables were about visualizing the hand over the device. And that will be a tool that you'll be using throughout the rest of the semester to make sure that, first of all, the device is actually seeing your hand and that you're capturing the right kind of data from your device. So in deliverable 3 and 4, over the next 2 weeks, we're going to be switching gradually from visualization to data capture, and then from data capture into machine learning. So the core component of your ASL educational system is if the user places a gesture over the hand, you need to write a machine learning algorithm that will recognize whether or not they are signing the gesture that they're being asked to sign, right? Okay, so let's talk a little bit about deliverable 3. The first part of deliverable 3 is actually capturing data from the device, and the data we're going to be capturing is data from a single frame. So I mentioned a couple weeks back, we're going to be focusing on just ASL gestures that are static. There are a few ASL gestures that unfold over time. It's a little bit beyond the scope of this course. We're going to focus on just recognizing the ASL digits between 0 and 9, and those 10 digits don't require any movement. So we're going to be capturing in deliverable 3 just one frame of data. How do we do that? Well, you're going to eventually have some code that will, like before, recognize the bones in the hand and draw them now in green. And when you bring your secondary hand, let's see if I can do this here. Hopefully you can see. When I bring my secondary hand into view, let's see if we can get this to work. Live demos, always a challenge. When I bring my secondary hand into view, you'll see that the green hand turns red, and red is going to be a visual metaphor for recording. The minute my secondary hand leaves the frame of view, let's see if I can get this to work a little bit better. There we go. You'll see it turns red, and then the moment my secondary hand leaves the device's field of view, it turns green, and at exactly that moment, we're capturing the gesture. So if I want to sign 0, I try my best to get the device to see that I am signing 0. That's a little better. Bring my secondary hand in, make sure everything looks good, and leave the field of view. And I just captured one clean frame of a lefty, in this case, signing the gesture, signing the sign for 0. Make sense? Okay, so you're going to be capturing a number of frames, and then at the end of deliverable 3, you're going to write a new Python program that will then read in the data that you've written out to disk and play back those gestures one after the other. So this is the video that you're going to be submitting at the end of deliverable 3, which is a series of captured frames. Okay. Usually I would have you actually capture the interaction of signing with your primary hand and recording with your secondary hand, but most of us don't have 3 hands to actually hold your phone and get some video of that, so we'll trust you in this case. You're only submitting this last video showing that you're able to play back the data that you recorded. Sound good? Okay, so let's talk a little bit about the data now. We're going to, in order to capture and manipulate the data, We're going to be using a new Python library called numpy, which stands for Numerical Python. How many of you are familiar or used numpy before? Most of you, but not all of you. That's fine. If you want to get a head start on Deliverable 3, if you haven't used numpy before, good thing to do is find an online tutorial and work your way through the basics of using numpy. Okay, so how are we going to tell numpy to capture data? As you know by now, each frame contains information about 20 bones, 4 bones in each of the 5 fingers. It's actually 19 bones. The 20th bone is this virtual thumb metacarpal, which doesn't actually exist, but we're going to assume that we have these 20 bones. For each bone, we're interested in 6 numbers: the x, y, and z coordinate of the base of the bone and the x, y, and z coordinate of the tip of the bone. So for each frame of data, how many numbers are we capturing? We want information about all 20 bones, and we need 6 numbers for each of the bones. 120, right? Okay. All right, so how are we going to store these 120 numbers? We're going to be storing them in a numpy 3-dimensional matrix, which I've drawn in cartoon here on the left. You may or may not be familiar with tensors or working with matrices that are larger than 2 dimensions. For a lot of people, the word tensor is scary. Don't worry, we're going to visualize it here. It's actually pretty intuitive. So we have 3 kinds of data. We have 5 fingers, 4 bones per finger, and for each bone we want 6 numbers. So you're going to be creating a numerical pi, a 5 by 4 by 6 3-dimensional matrix, right, which will store all the 120 numbers for us. As you can see here, when we do so, you're going to have a matrix that has 5 rows. Each row corresponds to one of the fingers. So the 0th row, if we cut through the 0th row, which are all the numbers in the matrix that are highlighted in red here, that top row, or that horizontal cut through this 3D matrix, contains all the 4 times 6, 24 numbers associated with the 0th finger, which according to leap motion is the thumb. The 4th, or the last row, corresponds to all the 24 numbers about the 4th finger. We're going to count 0, 1, 2, 3, 4 in this course. The 4th finger is your pinky finger. So far, so good? Okay. So this is a good figure to refer to from time to time because you're going to be switching now in Deliverable 3 from visualization, seeing the actual gesture, to looking at the data itself. And it can often be difficult to look at the numbers in this 3D matrix and make sure you're capturing the correct numbers. So you need to be able to understand how to navigate through this matrix and know which parts of this matrix correspond to which parts of the frame of data you're capturing from your hand, right? So again, in this cartoon here, I've highlighted the thumb and highlighted the part of the matrix where all the information about that is contained. If we're interested in information about just the distal phalange, the bone at the tip of your thumb, it's the last bone in the series of 4 bones marching outward from the palm to the tip. And that corresponds to the 4th column, right? So rows correspond to fingers, columns correspond to bones, right? So if I restrict my walk to the top row, which is all the information about the thumb, and then I walk outward from the first column, which is the metacarpal, second column, which is the proximal phalange, the 3rd column, intermediate phalange, and finally the 3rd and final column is the 3rd and final bone at the tip of the thumb. Okay, last one. I'm now focusing on the distal phalange in the thumb, and I have a total of 6 numbers, the x, y, and z of the base of that bone and the x, y, and z of the tip of that bone. And if I then ask for the 0, 1, 2, 3rd, 4th, and 5th numbers from that row and that matrix. I get back just 3 numbers which correspond to the x, y, and z coordinates of the tip of the bone. So far, so good? Okay, so you're going to be storing all 100 numbers from that flash when you take a picture of the gesture into a 3-dimensional matrix. And then the next thing we need to do is actually slice and dice this matrix to pull out different subsets of the numbers inside that matrix. So you need to familiarize yourself, if you're not familiar already, with numpy's slicing and dicing operations. So you're going to be creating in Deliverable 3 a variable called gesture data, and that variable is a pointer to this 3-dimensional matrix. And we can pull out different subsets of this data. If we specify, you remember that this is a 3-dimensional matrix, and because it's 3-dimensional, we need to add 3 coordinates to tell it which column, which row, and which horizontal stack moving from the front of this cube towards the back we're interested in. Okay? So in NumPy we start by counting down, then we start from counting left to right along columns, and then finally in the third column, in the third number here, we count from the front stack towards the back of the stack. Okay. Let's say I want to pull out all the numbers from the set of 120. I could place a colon in this position here, and a colon gives me tells NumPy I want all of the things that reside at this coordinate, which is all of the columns, rows, or stacks. Which one is it? All of the rows, right? Okay, so I want all of the rows. If I put another colon here, that tells me for all of the rows, I also want all of the columns. I'll just put an R, C, and S for stack here, just so you can build up an intuition for this. And finally, among all the rows and columns, I also want all the stacks. So if I were to store this extraction in a new variable, which I'll just call NV for now, tell me about NV. Is it a number? Is it a vector? Is it a matrix?
Exactly the same.
It's exactly the same, right? So NV is basically a copy of gesture data. It's got 120 numbers in it, stored in 5 rows, 4 columns, and 6 horizontal stacks. Let's say instead of pulling out all 120 numbers, I want to pull out just the 4 times 6, 24 numbers in this top stack, in the top row. I'm clearly not interested in all the rows. I'm interested in only one row. What row is it? The 0th row. Okay? So I tell it I want the 0th row, and inside that 0th row, which is this top horizontal cut through the matrix, I want all of the columns and all of the stacks. Right? So in new variable now, new variable will be a 2-dimensional matrix, and it'll be a 6x4 matrix, right? It'll have 24 numbers in it. Okay. If I'm interested in B here, I want information about just the distal phalange in the thumb. What goes in these 3 entries here, these 3 arguments? So 0 to start with, right? I'm still restricting myself to the 0th row. 3, because I'm interested in the 3rd column. And inside that 3rd column, I want all the things. So what goes in here? Colon, right? Okay. All right, so now new variable is a 6-element long vector. Pretty straightforward. Okay, last one, C. I want just the 3rd, 4th, and 5th number from the 0th row and the 3rd column. For those that are familiar with NumPy, what goes in here? 3:5. 5, right? So the colon by itself says give me everything along that dimension of the vector. And if I put a number before and a number after the colon, I'm specifying a range along that dimension, right? New variable will now be a 3-element long vector, which will be just the x, y, and z coordinates of the tip of the distal phalange in the bone. Okay. You'll get lots of practice in Deliverable 3 and Deliverable 4, slicing and dicing and extracting different subsets from this 3-dimensional matrix. Sometimes it's easier to set if you're not comfortable with this kind of notation, sometimes it's worthwhile setting your code aside, creating an empty Python script, creating an empty 120 element 3D matrix, and then doing what we just did, pulling out different subsets and printing NV, printing the new variable, and making sure you're getting back exactly what you think what you were expecting to pull out of the matrix. Sound good? Okay. Any questions about Deliverable 3 before we push on? All good? Okay. So as I mentioned, in lecture 4, we're going to start by introducing this concept of design. Design is a central part of HCI. Why are we going to spend so much time talking about design? Because a good way to do HCI poorly is to not design and dive in and say, what can I do with this new whiz-bang leap motion device? There's lots of things I could do. Let's try it. Rather than stepping back and designing software for it that supports as many different users for the tasks they want to carry out. Okay. How's that in the back? Can you see the bottom of the screen? Yep. Okay. Okay, so we're going to talk in this course, in this lecture, about 4 different aspects of design. Design philosophy, design process. We're also going to talk about design principles and design parameters. Unfortunately, they all are design P something. So by the end of this lecture, make sure you can distinguish between these 4 different aspects of design. Well, what is design itself? For our purposes, we're going to think about it as an act of translation. We're going to translate X into Y, where X is some need on behalf of a user or set of users. There's something they'd like to do, which is difficult or impossible without the technology you're about to deploy for them. So they have this need, and we're going to try and identify and clarify exactly what that need is, and distill out of that need or translate it into a physical structure. It may be a process, it may be a combination of hardware and software, some artifact, and we're going to try and carry out that translation in the best way possible. So the translation itself is the design process. We've identified some need, and eventually we're going to end up with some hardware and software. That's a process. There's lots of different ways we might go from desired need to finished product, and depending on our particular design philosophy, we might see some of those processes as better than others. If we got a whole bunch of people together and said, here's a need, and here's our sketch for a final product, tell us all the different design processes you can imagine. That group as a whole might sketch out 10 or 12 or 15 or 18 different design processes. We might then ask the group which is the best one, and the group may disagree because the group may have different ideas about design philosophy. Right? It's the difference between design philosophy and process. Okay. We're going to have a look now very briefly at design philosophies and processes across lots of different domains. And we're going to start by looking at the most subjective domain, which is the artistic or aesthetic domain, where there are little to no constraints on how we carry out some need, perhaps on the part of the artist, into a finished painting or sculpture or what have you. And we're then going to march from very subjective domains of human endeavor to increasingly objective domains of endeavor, where we can sit down, or our users can sit down and say this product is designed well or poorly. Right? We're going to get more of an objective viewpoint back from our users about whether this product works or it doesn't. As I mentioned before, and you probably figured out by now, HCI really sits somewhere in the middle. It is not a purely technical discipline. This is not a software engineering course. We need to create software that's bug-free and runs quickly and runs on as many platforms as possible. But that's often not enough. We need to have software that's not just correct, but somehow subjectively appealing to users. They want to use it. They will choose your product over another one. So in the middle here, we're going to look at some domains of human endeavor which also try and juggle subjective and objective constraints. Okay, so let's start with fine art. And again, I'm not an expert. We can talk about some design principles now. Not design philosophy, not design process, but design principles, which we'll think of as sort of rules of thumb. Something you might want to try and apply when you're creating sculpture or paintings or what have you. What are some of the principles of beauty that you might apply as you try and create beautiful works of art?
Symmetry.
Symmetry, okay. What else? Some of the examples I've added here are symmetric, some are not. We're in a very subjective discipline here, obviously, so there's lots of different principles we might bring to bear. Contrast, symmetry, contrast. What else?
Maybe novelty.
Novelty, okay, absolutely. Some of the paintings or works of art here at the time that they were introduced were pretty novel and controversial and surprising. What else?
Meaningful.
Meaningful, right? Okay, so symmetry is pretty easy to nail down. You can say whether something is symmetric or not. To say whether a particular work of art is original or novel in some way, it's a little bit more difficult. Meaningful is, again, extremely subjective. But you'd be surprised, right? A lot of people will, a large group of people will agree this is a meaningful work of art. Even for things that are very subjective, you can start to see that it's appealing, maybe not to everyone, but to a relatively large group of people. What else? Any aspiring artists here? Okay. Here's a few that I wrote down. Obviously, we could probably spend all day and all semester making a laundry list here. Some of these were already mentioned. Balance, symmetry, proportion. These are sort of the first lessons if you take a fine art class. Color, originality, resemblance to natural structures. This was a guiding principle in Western art all the way up until the 18th and 19th century. Visual impact, perspective. If we go back to the Western Middle Ages, maximize ornamentation, the Baroque period, and so on. Okay, so those are some sort of rules of thumb that have applied, at least in the history of Western art. Let's take one step towards more objective studies, visual design. You've seen this picture already. This is from the Gapminder website. It is not meant just to be pretty, but also to do something else, which in this case is communicate information. But in order to support this need, which is to communicate information about health and wealth, we can still apply some principles drawn from the visual arts. There's some things that we might want to apply here. What are some of the principles of visual design? What are some of the principles of design that are on display in Gapminder?
Contrast.
Contrast, absolutely, right? That makes sense. Little to no contrast, definitely not going to make sense here. In certain domains of fine art, maybe contrast is not so important. What else? Yes?
The ability to comprehend what you're seeing.
The ability to comprehend what you're seeing, right? So that's a requirement of the system. That's a function we're trying to support. What principle of visual design helps with that? I'm trying to understand what this picture is trying to tell me. Contrast helps me see that picture. What else does? Perspective. How so?
You mentioned last time that the overlook plane glass represents, for example, the
Absolutely, right? So dots lying on top of one another, dots that are closer to you are closer in time. So there is an assumption here about perspective, right? I can't see information about China in 1975 as well as I can see information about China in 2004. At the end of the list here, I put maximize ornamentation. One of the guiding principles that most visual designers would agree on is minimize ornamentation. One of the things I like about Gapminder is if you think about the RGB, the red, green, blue components of every single pixel in this plot, it's all doing work for you. There is an attempt to include no extraneous color or detail that's not absolutely necessary for helping to communicate health and wealth in China versus the US in this picture. That principle we'll come back to later in the course, which is often known in HCI design or visual design as maximizing the data to ink ratio. We want to maximize the amount of data that we communicate to the user, but use a minimum of quote-unquote ink to do so. Right? We could try and communicate a lot of information with a lot of complex graphics. That doesn't work so well. We could simplify the graphics, and if we're not careful, we might simplify the graphics and throw the baby out with the bathwater, remove some of the data as well. What's very difficult in visual design and HCI is to simplify the visual presentation and increase the amount of information that's communicated. Right? In Deliverable 2 that you just finished, you're drawing these 20 lines, and as you saw probably partway through the deliverable, it was often difficult to see the orientation of the hand until you started to broaden the width of the lines, right? So we added a little bit more ink, but we added just enough to try and help the user see that this is their actual hand and this is their virtual hand. Right? We're adding just enough ink to communicate the information that we need. Easy to say, maximizing the data to ink ratio, often very difficult to get right. There's sort of a general principle that you can pull out of visual design and apply to HCI. Okay, I love this animation. Let's see if it'll run. This is a little GIF showing how to improve the readability of this table, which is communicating very important information. Throughout this GIF, they are removing things. They are removing ink, but removing little to no data itself. Even in something as simple as a spreadsheet, there is a lot of work you can often do and little sort of tricks from visual design to clarify the information that's presented. Okay, less is more. Okay, so let's move on now to architectural design. So this architecture is interesting because, like HCI, architecture tries to straddle the objective and subjective, right? We all have to spend a fair bit of time indoors. We would like that to be as visually appealing and as comfortable an experience as possible. So the objective side of architecture, build a building that doesn't fall down, but do so in a way that is appealing and engaging to users. Architecture is also very far from HCI. It doesn't have much to do with software, at least not most of the time. But they both have to address this challenge of reconciling the subjective with objective. Okay, so here are two very different buildings. The building on your right, there's an outside and inside view of the building. Which two buildings are these? The building on the right is a Frank Gehry building. Which one?
The Bilbao one?
No, not the one in Bilbao, Spain. It's a lot closer.
Isn't that a dorm in Boston?
It's getting closer. Yes, it is in the greater Boston area. It's actually in Cambridge. It's a strong hint.
MIT.
It's an MIT building. It's a Frank Gehry building. It's an MIT building, getting very close. This is the Stata Center. This is the home base of MIT's AI lab. Next time you make it to Boston or Cambridge, it's a wonderful building to go and visit and walk through. As you mentioned, it's a Frank Gehry building, which is instantly recognizable for most fans of architecture by the outside of the building, which is all curves, or a lot of curves. Not so many curves indoors. Why not? Doesn't make sense. Why does it not make sense? You can't use curved surfaces for much indoors. Why not? I can make curved floors and curved walls and curved ceilings.
Because humans use like level surfaces.
Absolutely, right? Which in retrospect seems obvious, but this game we just played is something that comes up over and over again in HCI, right? A user makes use of some software and said, this is impossible, this is terrible. Why is it terrible? Because I always expect to ... I always expect to walk on a floor that's perfectly flat. I may be able to walk on a floor that's curved, but if I'm in a wheelchair or I have limited mobility, it may be extremely difficult, right? So you can sort of see how Gehry and other architects reconcile the subjective with the objective. The outside, you have less constraints. There are obviously still constraints. If you spend any long period of time in the status center, whenever it rains heavily, there are always leaks. One of the most popular robots you'll see on display is the status center is a wall climbing robot that will go up and put some duct tape on a leak in the ceiling. Okay, what about the building on the left?
Sistine Chapel.
Not the Sistine Chapel, but again, about very close to it. About a 2-minute walk from it. St. Peter's Basilica, that's right. Two extremely different buildings, built in different cultures, different ages, but they both try and do the same thing, reconcile the subjective with the objective. Two very different processes, but two very different design philosophies, right? You may find neither building appealing, but for some people, there is a certain tradition about how to build architecture, and for others, there's a very different tradition. Okay, let's keep going. Let's move, again, one step towards more objective design. Engineering design usually has a lot more constraints than architecture, but assuming you have a little room to maneuver, you can also try and address aesthetic conditions here. So let's look at some possible design principles, which again are sort of rules of thumb here. One design principle is we want to try and separate functions within the artifact as well as we can. And that principle comes from a particular design philosophy about the right way to design things. What is the design philosophy that says it's a good idea as a rule of thumb to try and separate functions within an artifact?
Simplicity.
Sorry?
Simplicity.
Simplicity? Maybe. We might have lots of different functions. Not necessarily simplicity. Modularity, right? So a guiding design philosophy, which often goes unspoken in engineering design and software engineering design, is modularity. There's lots of different design processes that support that kind of philosophy, separate functions within the artifact. Okay. It seems so obvious to most of us, we don't often see it's there, but if we're not sure that it's there, you often miss it when you go to design your own software or hardware. It seems ridiculous to design a car where that car has different modules, maybe somewhat modular, but module X inside the car partly helps with smooth transport and motion generation, and so does module Y, but in a slightly different way. Right? We want to pull out orthogonal function, very different kinds of function. In a car, for example, we need to translate chemical energy, fossil fuels usually, into motion. That's one important function. A second function is to translate that motion into smooth transport of the vehicle over flat terrain and so on. So we start in engineering design usually with functional requirements, and we'll see that again in software engineering in a moment. The system should do X. We then apply our design philosophy, which is modularity, and we formulate a design process or principles where we're going to try and create something that does X by creating module components where each of those module components carries out some distinct function. And one way this is described as creating a series of functional requirements. Here's a set of 2 functional requirements for this very complex machine you see on the right here. Functional requirement 1, the device, whatever we're going to build, it should be able to open cans, and it should also be able to open bottles. Sorry, I misspoke here. So we have one functional requirement, open cans. We then take that functional requirement, which we've separated out from a second functional requirement, which is that it should also open bottles. We take the can opening functional requirement and turn that into a design parameter, the 4th design P we're going to see today. And the specific design parameter here, the subscript tells us that this design parameter supports this functional requirement. If we want to open cans, we're going to do so by creating something that has a sharp point for puncturing the top of the can. Okay. So we create 2 functional requirements. We have 2 design parameters, one that describes this thing and a second design parameter that describes this thing. We put them together on a metal bar and we have the world famous bottle and can opener. There is a constraint that is now built into this device which has gone unspoken. What is the constraint? The user has to have a hand. Okay, so there are lots of assumptions about the user, which again is good HCI design for you. Forget the user for a moment. What is some constraints that have now been built in given this set of particular design parameters we've settled on? This device itself.
The device needs to have space for a user's hand?
It has to have space for a user's hand, right? Exactly, so we're going to separate them just by about a hand width. What else? Obviously, I want to use this to open cans and bottles, but there's a bit of a constraint here.
Should it puncture your hand when you're trying to open a bottle?
Okay, that's true. Hopefully it's relatively safe.
It has to not break.
It has to not break. Okay, so that's possible. Yes? It has to fit the cans and bottles, absolutely. So there's probably a growing set of other functional requirements and design parameters.
It can only open one or the other at a single time.
Exactly, right? We have a sequential device. I can't open cans and bottles at the same time, which is maybe not something I want to do most of the time, but it's in there, right? It's implicit. And this is, again, part of HCI design. We want to take these implicit assumptions and implicit constraints that we've now introduced to our product or our design and make them explicit. The system can open bottles and cans, but it is not required to open both at the same time. We may loop back to our requirements and rewrite our requirements.
When does that design become too much of the Swiss Army knife that just got too big?
When does it become a Swiss Army knife and it's got too many gadgets on it, it's too complicated? When? When do we know that that's happened?
When it becomes no longer useful?
When it becomes no longer useful. Okay, useful is a vague term. Can we do better than that? When the user says so, or the users, plural. Absolutely. I don't know. Is two devices here too many, or 2 widgets, 3, 12, 18, who knows? It's up to the users. We're going to spend a lot of time talking about user testing in this course. Okay. Let's move on to software engineering or software design. As the name software engineering implies, it derives most of its design philosophy from engineering itself. And the main design philosophy that underlies most of software engineering is, again, modularity. Right? We would like to make things as modular as possible. However, there are additional design principles that you often find in software engineering that are not so ubiquitous in engineering itself. There are many, and people disagree about these principles. One of my personal favorites is iterate tightly and often. You've probably already figured this out by working your way through the deliverables that I am the author of, is that a lot of times you're creating a new Python program that has one line in it, print 1, right? Seems like a ridiculous thing to do, but For those of you that grew up writing code in Python 2, that's a perfectly valid statement. And as I learned when I migrated to Python 3, not okay, right? So even writing something like this, you often get an error message. Luckily, I'm okay here because I'm using Python 2. As you can see, I've named my piece of code adding, so I want to write a piece of code that adds. And here we go, another live demo for you. What's going to happen when I run my code now? Hopefully it won't crash. It's still going to print 1. So I'm not just writing code, compiling and debugging. I also have a mental model about my code, and before I run it, I have a prediction about what it should do. And if what I see doesn't match my predictions, there may be some implicit assumption that I've made that's wrong, something above and beyond just bugs. So let's verify that that's the case. Looks good. Okay, I want to add numbers together, so let's define a function. I don't really know what's going to go inside this function yet, so I'll just put a pass statement. When I run my code now, what do you expect to see? Same thing. So far, so good. Reality is matching my expectations. I'm going to call this now. What do you expect to see? Okay. Looks good. Okay. Still not sure, but I'm going to put a little bit of function in. What do you expect to see now? Looks good. What do you expect to see now? One time. Gotcha. Yep. Okay, now I'm a little more comfortable in what I want to see. What are we going to see now? Same thing, right? I made a little misassumption here. That's what I want to see. Okay. Finally clean everything up. Looks good. Okay. So you may find that particular design principle ridiculous. Why would I iterate so many times around such a simple piece of code? But at every point, I have an expectation or prediction about what I should see, and I'm checking to make sure it fits. When I was doing my master's degree years ago, we had a one-year master's program where we spent the first 6 months taking classes, and then the second 6 months was a big programming project. I had a friend in the class. He knew he had 6 months. He spent the first 5 months writing code, but never compiled it. And he assured all of us he had a whole month at the end to compile it and work out the bugs and make sure everything worked. So he had a very different design philosophy, which is iterate once, right? Or iterate at the end. Unfortunately, my friend never finished his degree. Okay, just a warning for you. All right. Okay. So there's a design principle, one design principle that I'm a fan of, iterate tightly and often, and I'm going to force you to do that through the next 7 deliverables. For the final project, it's up to you, obviously. As you become better coders, you will build up your own design principles and your own design philosophy about how to write good code. In the early decades, or the early years of software engineering in the 1970s and 80s, there was a particular process. And remember, design process is the actual translation from identified need. We sit with our users, we get them to tell us what they want, and we turn that down into a written set of requirements. The software should do this, and it shouldn't do that. We then design the system architecture down to a very fine-grained level of detail. When we have a very detailed design, we can take that design and relatively painlessly turn that design into actual code and test it and validate it, and then finally deploy to the users, and we're done. What's wrong with the waterfall method? At least if you agree with my design philosophy. You're already, right. And the idea at the early days was, yes, we're only going to do it once, but we're going to be very, very careful at each of these steps. It's a waterfall method. We are going to hold back from going on to the next step until we're absolutely sure exactly what our software should and shouldn't do. Sounds good in theory, very difficult to get right in practice. So there was a big movement that militated against the waterfall method known as agile methods. Lots of different agile methods out there. So in the 90s and 2000s, it was all about agile programming. I don't know what's fashionable these days, somewhere in between. Okay. Finally, we're moving into the design of interactive systems. So now we're going to be looking at design principles that are specific to HCI design. In software engineering, we may be developing code that's only ever going to be used by one person, or it's going to be running on a server locked away in a room somewhere, and unless it crashes, nobody's using it. It interfaces with other pieces of code. That's fine. We can apply software engineering design principles to it. If, however, the software or software hardware system that we're designing is going to be used directly by users, and especially if it's going to be used by large numbers of people and diverse kinds of people, we need to not just create software that completes the desired function. It has to do additional things. It has to also maximize certain global properties of the system itself. The system has to not only be correct and not crash and run quickly and run on lots of different platforms, it also has to be accessible, usable, acceptable, engaging, and so on. We're going to distinguish in this course between functional requirements. These are statements which we might write down, which are about the function itself. The system should open cans and bottles, but not necessarily both at the same time. Those are functional requirements. We may add on top of that what are known as non-functional requirements, and they're called non-functional requirements because they don't directly relate to the functions themselves. They're about some global property of the system. So we might want to build a bottle and can opener that isn't just a simple blade of metal. It's got some color, it's rounded, it looks cool, it's humorous, it's whatever. There may be something we add on top that if someone walks into a store and sees this can and bottle opener and our can and bottle opener, both open cans and bottles, but ours is much more engaging and they'll buy ours. Okay. Non-functional requirements are particularly difficult to get right because they tend to be vague. How do we make something that works well and is also engaging, draws the user in? What exactly do we mean by that? The biggest challenge most of the time in HCI design is nailing down these non-functional requirements and validating that they have been instantiated in the system itself. Okay, how do we do that? Well, now we've got to switch back to design process. In HCI design, there is definitely not a waterfall model. Usually it looks something like this. At the center here is evaluation and user testing. On Thursday or maybe next week, we'll talk about these other 4 elements of HCI design. But throughout the design process, at every stage of the design, starting with simple prototypes and starting with even before the ink is dry on the requirements, even early on, we're going to the users and we're asking them or showing them, is this what you have in mind? Is this what you have in mind? What do you think about this? Do you prefer A or B? Turn to another user, do you prefer A and B? And so on. So we're always returning to the user. Let's have a look at some of these non-functional requirements. They're very vague and somewhat subjective. So what we're going to try and do is take each of these 4 broad categories of non-functional requirements and turn them into objective statements. And then finally, once we have them as objective statements, we're going to turn them down into measurable statements, something we can measure with our users. We could create a piece of code and put it in front of our user and ask them, is it engaging? Did you like using it? Was it fun? What's the kind of response we're going to get to that question? Yeah, exactly. What am I going to do with that piece of information? What is yeah mean? Am I done? I got a yeah, that sounds like a yes. Can we be more specific than that, right? So what we're trying to do is not just elicit answers from our users, but figure out what the right questions are to ask them during user testing. Again, not an easy thing to do. Let's start with accessible. We'd like our system to be accessible to everyone on the planet, or as many people as possible. Sounds good. How do we do that? One way to do that is to start in the case of accessibility and flip it around and ask the inverse question, who's excluded from the technology? Okay, as we mentioned last week, there's lots of different dimensions to human diversity, so lots of different ways in which people might be excluded from technology. Some of them are kind of obvious, and some of them are much less obvious. So let's start with the obvious ones, physical exclusion, right? The height of a keypad on an ATM machine is very important. We want to make it low enough that someone can use it. Do we need to make it low enough for a child to use? No, because a child probably isn't going to be using an ATM machine, we hope, right? But someone in a wheelchair may. So there's some obvious things there about ergonomics, the fit of the device. Where do we place the keypad, the monitor? How do we angle the monitor? Should there be speakers? Lots of things we can think of there to make sure that we minimize physical exclusion in order to maximize physical accessibility. Those are pretty obvious. Less obvious are conceptual exclusion. When we talked about conceptual modeling last time, this idea of a mental model. People often approach technology with an idea of what it is and how it should work. And if their expectations are not met, they're confused or frustrated or what have you. What they're looking for when they're interacting with the system is cause and effect relationships. I don't know how many of you have had the wonderful experience of teaching elderly family members about the difference between 2 slow single clicks and a double click. It's obvious, right? I've spent a lot of time with my father trying to get that one right, and after 35 years, I've thrown in the towel. Forget it. He's never going to understand the difference between 2 slow clicks and a double click. What are some other examples of those kinds of cause and effect relationships that are difficult to communicate for certain groups? We've all been raised on technology. It's pretty obvious to us, but there are other groups where it's not so obvious. You think of some other distinctions? Left click, right click, okay, that one's kind of obvious. Single click, double click.
I know, like, I've interacted with older people who don't understand the difference between, like, the internet and Yahoo, or the internet and Google, or how those are related.
Absolutely, right? What's the difference between Google, Safari, the internet, the web? Not so, seems obvious to us, right? One is a system, another one is a window through which you see that system, and another one is a particular instantiation of a particular kind of window. It's a great example.
I don't know how I concisely kind of explain this, but my brothers are working on a game with a local game company, and they did testing, and he brought his elderly friend, and part of the game, which probably a lot of people are familiar with, is you use the WASD keys to move and the mouse to look around.
Okay.
And his elderly friend couldn't really get that you could like do multiple of the same thing at a time.
Exactly.
So
That's
he'd walk forward with W and then look, kind of point where he wanted to go, and then so it was very much one and then the other, and not.
That's a great example, that you couldn't do both at the same time, right? Which already builds on top of another expectation, which in a lot of games, you're using your left hand for the keys and your right hand for the mouse. Keys are usually about movement. The other one is about looking, staying in place. That's sort of a common expectation. The fact that you could do them both at the same time is not so obvious to everyone. Another example?
The idea of like the cloud and
what is the cloud, right? How many family members have asked that? I'm sorry. Yeah. What exactly is it, right? Is my cloud in here? Is it out there? Where is it?
I'd say most organizations are under conceptual exclusion when they specialize in a certain area.
When they which, sorry?
When they specialize in a certain area.
Okay.
So you'll see like an operations team be like, why are you using people that way? When human resources is hiring people. Like there's always this conceptual exclusion that's going on in some way. I think most conceptual companies figure out methods for communicating those students.
Absolutely, that's a great example, and figuring out ways to make it explicit and communicate that, right? So for most technology, we're never going to get exclusion down to 0, but what is our threshold, right? Where are we trying to get to? Is there can we actually turn these ideas into something that's actually measurable? We'll talk a lot about measurement when we get to talking about user testing. Okay, some other ones, obviously, socioeconomic status is their economic exclusion. There was a big movement about 15 years ago known as the 1 laptop per child. And the idea here is, could we create a laptop that costs $100 and get as many laptops in the hands of young people in the developing world as possible? You can go read about 1 laptop per child. It's a very interesting case study in HCI. Another subtle one is cultural exclusion, right? We talked about forward and back buttons and reading left to right and right to left. Are we making inappropriate assumptions from our own culture and building them into the technology itself? The history of software development is littered with these kinds of examples, and I'll just show you one. It's an example of cultural exclusion. Again, this is from the 1 laptop per child. The idea here is we want to have a very inexpensive laptop, and we're going to be placing this in the hands of children in small villages in the developing world, which, again, before the YouTube era and the smartphone era, you could safely assume they hadn't seen a lot of technology up until this point. So we better make sure that the user interface is as simple and obvious as possible. With the exception of this up here, there's no English text on the screen. You can be pretty sure that for most of the users of this, they will not be able to speak or understand English. This is the Sugar user interface. There are a number of icons here. Imagine you are a young child in the early 2000s in a small village in South America, and someone puts this machine in your hand, and you turn it on, and you see this. What do these 3 icons mean to you?
I mean, anything, right? Like every single combination, you just start trying every single thing.
You could just try, we say, I don't know what they mean, let's try them and see. We could do that, which probably most young people will. What might they think they mean?
The one with the 3 bars looks like a network. Like that's why the Wi-Fi.
It looks like a network, that's probably where the Wi-Fi is coming from. You might think that.
Right.
A young child in a small village in South America that has seen little to no technology before, this is a great point, right? You are going to see something very different from what they are going to see. What are they going to see?
This isn't really something with the icons, but it kind of looks like a football game. It's something.
Looks like a football game. Okay, so maybe you might interpret this as soccer. Yeah, exactly. Which is, it's not meant to be. Yes?
To me, it looks like a wheel, but they might see it as a wheel.
Which one? I'm sorry.
The first one that the mouse is over.
This one here?
No, sorry.
Oh, at the top, this one up here. Yeah, who knows what that means? It's pretty abstract. Let's go back to this example here. What about this particular icon here?
Like volcano.
Volcano, right? They picked South America on purpose, right? Not only do a lot of children, again, depending on where they are in the world, if they haven't seen an icon for a wireless tower before, if you see a big triangle with stuff coming out the top, that's probably what it is. The Sugar interface was designed to communicate to the users that they should move towards this thing. If you need Wi-Fi to power your device, instead of explaining what Wi-Fi is, just show a picture and show animations of people moving towards it. Imagine you receive one of these machines and it seems to be telling you to move along with your friends towards the active volcano. Super acceptable, right? Makes perfect sense.
Is this a map? Are all these X's are the people?
Exactly right. It's also confusing to us. I'm not exactly sure. I know some parts of this. And not to pick on the Sugar interface, very difficult to get this right if you're trying to communicate to a very different demographic to yourself. What about this one down here in your bottom left? What does that mean?
It almost looks like one of the paintbrushes things when you click on it and then you take it off.
Exactly, right? It's a paintbrush with an easel, of course, right? That one's not going to be a problem.
Unless you hadn't seen a paintbrush before.
Paintbrush or an easel, that's, again, a Western assumption. That means art, right? That's what it is. Okay. Lots of examples of this you can find of where HCI is not done exactly right. Okay. Social exclusion, again, who's going to be using this technology in what place? Are we getting them to all sort of crowd around a Wi-Fi tower or a node or some sort of limited resource? Maybe it's easy to use this on its own, but not so easy when everybody's using it at the same time. I just got back from the UK, and there's a great story about this from the UK. Not so much about software, but the power consumption in the UK, it spikes once a day. Power consumption spikes so high that France has to supply energy to the UK during these short few seconds of spike in power. They need to be so ready that operators in France that are at the power station that are getting ready to supply are watching a particular device to know exactly when the spike is going to occur. What causes this spike in UK power consumption?
Isn't it people turning on their tea kettles during like soccer breaks?
Exact. People turning on their tea kettles during soccer breaks. The version that I heard is when Coronation Street, the very famous soap opera, ends. I'm sure it's also football games. Exactly. So in certain France power stations, they have a big screen at the front that's playing a particular channel of BBC. Okay. Okay, so we'll come back to accessibility in a bit. Let's move on for now to usability. So usability, we want to make the system easy to use, which again, at this level of detail is pretty vague. So can we start to try and unpack this into more specific terms and eventually objective terms, and then finally into measurable metrics? Lots of different ways of unpacking this. We want something to be easy to use, easy to learn, flexible, and people like to use it. When they're finished, they're not frustrated. They feel that they efficiently got the task done. So efficiency is usually a part of usability. If something isn't efficient, it's not very usable. Effective, slightly different from efficiency. Do they have the right functions in place to carry out what they want to do? They may not be quite right. So I want to do X, and the technology is very efficient. It gets me very quickly to X prime, but X prime is slightly different from X. It's not exactly what I wanted to do. It's about 95% of what I wanted to get done. You're going to deploy a system to teach users ASL. It's not actually teaching ASL, it's teaching the first 10 digits of ASL. You're going to try and create a system that teaches them just those digits as efficiently as possible. But in terms of teaching ASL in general, it's not going to be very effective. Okay. Easy to learn how to carry out the task using the device. And is it also easy to remember how to do it? Assuming the users are going to come back to your technology multiple times, are they going to remember how your system works the second time around? We'll talk more about learnability and memorability when we get to the psychology component of this course, but what are some general things that are kind of obvious that make something learnable or memorable? Repetition, right? So we could force our users to use the system many times, although that might militate against acceptability. They don't find it acceptable. They're being forced to do something over and over again, which is a good way to learn something, but there are other ways.
Teach how the system works to other test subjects.
Have them teach it to other test subjects?
Yeah.
Could do that. Maybe we could sort of try and crowdsource this somehow.
If it's analogous to something that they already use.
Absolutely. If it's familiar, then there's relatively little I need to learn, right? For most of your users, the Leap Motion device is going to be unfamiliar, but you can project things to the screen that hopefully make the system familiar, right? Can we make things as familiar as possible so they only need to learn the minimum of new stuff, right? We don't want to try and reinvent the wheel here, right? So we can bypass repetition and make our system a little bit more acceptable if we make it familiar. What makes something memorable? It's easy to remember when you come back to it, how to use it. Familiarity helps here as well. What else? Uniqueness, right? Which is kind of the opposite, right? Here's the new thing, and here's how you use the new thing, and I'm going to try and present it to you as simply as possible so you remember the next time around. That's great. Okay, safety, this one's kind of obvious, but not so obvious when we think about different people carrying out different activities in different contexts. For a certain group of people and a certain version of the activity in a certain context, it's very safe. For another group and a different activity in a different context, it's absolutely not safe at all. Can anyone think of any examples of that? What are some examples of technology that are safe for 99% of the people and the activities and context, but there's 1% where it's very unsafe? Texting, right? Texting while driving. That's a great example.
Drone flying.
Drone flying, absolutely. Lots of emerging contexts that we as a society are learning about where it's not so safe. Okay, utility, this one's a little bit tricky. It's, again, related to efficiency and effectiveness. It does the things people actually want to get done, right? So we're not, again, deflecting them away from what they're actually trying to do. Okay. So let's dig down a little bit further into usability. How do we actually start to turn these things into measurable metrics? So now we're kind of focusing again on design process. Throughout HCI, we'll see this in different ways. We want to focus early on users and tasks, early in the design process. It's very hard towards the end to fix a system to make it more usable. We want to try and include the users as much as possible in the design process itself. We can do all the coding and then ask them questions, get back responses, and alter the code, rinse and repeat. Or we can invite the user into the design process itself. Measurement, I've already mentioned this. Instead of asking them, did you find the system to be usable or not, we want to try and record and analyze users' reactions to the prototype. Often we want to do this non-verbally. We want to observe their behavior directly rather than ask them what they thought. It turns out that in the system you're developing with Leap Motion, this is not so difficult to do. What are some measurements you might be able to pull out of your user's interaction with the Leap Motion device, where those measurements will tell you whether they understood what they were supposed to be doing or not?
I mean, my thought was to create a dictionary, so I take coordinates for each of the characters for lots of different people in the first place that already know it.
Okay.
From there, I'll start creating like a standard deviation, and that will give you some information about the coordinates on hand for that particular character.
Okay.
And people that fit within that deviation should be able to fit within the dictionary's definition.
Okay, so we can look at gestures recorded from different people and look at the standard deviation of where that gesture was captured. Maybe that gives us some information. Maybe people are putting their hands at different places in the device's field of view. We could record that information. What does that tell us about how usable the system is? Yep.
Well, I was going to suggest that as a user uses the system, if the accuracy of their gestures increases faster versus slower.
Okay, absolutely. So the accuracy of their gestures, if we're asking them to sign the digit 0, how long until they successfully sign that digit? And when we develop your machine learning algorithm next week in Deliverable 4, we could use our machine learning algorithm to tell us it took this long until they successfully signed the gesture.
So you can monitor how long it's being used in general.
Monitor how long it's being used, right? Yep.
Also, you should filter out noise.
Filter out noise?
High frequency data,
Okay.
which could be the system bugging out. You just don't take those data points.
Absolutely. We could, following that example, we could measure the amount of seconds between turning on the system and how long until until the Leap Motion device captures its first frame of data. How many seconds until somebody figures out, we don't want you to lift up the device or shake it or put your face over it. We want you to put your hand over it. How long does that take? If it takes a long time, it might be because our user is confused, the system isn't very usable, or it might be noise in the system itself, right? It gets tricky. So are there other metrics we might start to bring in that would validate that first measurement? It would help us decide, it would help us to determine, was the user actually confused or was it just noise in the system. Maybe they did have their hand over the device, it just took a while until it was recognized. Okay, let's move on. Iterative design, again, this idea of iterating tightly and often. When we're dealing with HCI, user testing is part of that process. When I was doing this coding demo for you, I was the user. I was making predictions about what I would or wouldn't see. In HCI, it's usually not just the author. Okay. We want to try as best we can to optimize all these factors together, which is extremely difficult to do in practice because all of these factors are interdependent. So I'm going to where improving one may adversely impact the other and vice versa. So let's back up for a moment and look at these 5 different usability factors. Can you see some examples in there where improving one of these usability factors hurts the other one, and vice versa?
I always find making systems easy to learn in the forefront causes a lot of efficiency problems because of how you think.
Okay.
More than just how the design is.
Okay, so maybe making something learnable makes it less efficient. We may want to actually repeat. We want to make sure that our user learns the system because we want it to be very safe, for example. Requires a lot of repetition, not very efficient. Efficient from the point of view of getting the user getting done what they want to get done, but efficient maybe at a higher level of optimizing all of these elements. Other examples of interdependencies here?
If you have something that's super specialized, in order for it to be effective, it probably is not going to be easy to learn.
Absolutely, right? So we want to help our user carry out a new task efficiently, but it's a very new kind of thing that people aren't very used to doing. Some other examples?
Going off of that, if it's super specialized, it might not have very high utility for other problems.
Absolutely, right? So it's very specialized. It allows the users to carry out one very specific task, but for most of the other users, it has low utility. They're not interested in this one specialized task. There's something else they're trying to get done with your technology, and it's very difficult to do. Okay. You will see a lot of these interdependencies start to rise to the surface as you carry on with your deliverables. Okay. How do you know when you're getting there? Already we mentioned user testing and measuring things. One of the interesting things you can see in the history of technology is, again, human psychology at play. Often if you observe people using technology or ask them about it, the way they talk about the technology or the way they use it will give you a hint for how usable, accessible, acceptable, engaging it is. One example of this, for example, is physical technologies like a hammer that are very simple, easy to use, learnable, memorable, and so on. If you ask somebody who's using a hammer what they're doing, they often don't say, "I'm operating a hammer." They say, "I'm hammering." Right? If you ask somebody how they got to class, they won't say, "I operated a vehicle to get here. I drove here." Right? So when the technology is good, people often verbify the technology itself. What are some examples of verbified technology? Googling, right? Number one example.
I think that's the same thing, sure.
Skyping.
Photoshopping, but Adobe doesn't like that.
They don't like that? Why don't they like that?
Because they don't want to lose the copyright to Photoshop.
Ah, interesting. I didn't know about that one. That's a good example. Okay. All right. The opposite is when the technology doesn't work, and now I'm no longer hammering or driving. Something didn't work, and obviously it can't be my fault, the operator, right? It must be the thing. It's no longer a verb. It's demoted back to a noun, right? Google's not working. It's not, I don't know how to Google. It's the thing that's the problem. So often the easiest thing to do is ask the user, do you like it? Do you not like it? Was it efficient? Was it not efficient? Often you can get more information from them by coming at it from a different angle. You can ask them to talk about the device, and they'll often give you hints in the way they talk about the technology that will give you a hint if you're on the road to usability or not. Okay, I'll leave you to think about some more examples of that. We'll stop here for today. You have a quiz due tonight, and most of you are working on Deliverable 3. Thanks.